Okay, in this example, we're going to look at a fairly simple unbalanced Y load and look at how we determine currents in this load, what the relationship between currents and voltages are, and how to find the neutral current. That's probably the toughest thing to find in a circuit like this. I have the circuit drawn up on the board. This load in phase A has a resistor of 15 ohms. In phase B, it has a coil with a impedance of 20 ohms at a power factor of 0.866 lag. And in phase C, we have a 12 ohm resistor. The supply is 208 volts. From what you have here, pause this recording and find out what the phase currents are for this load, for each phase A to N, phase B, phase C to N, and draw a phasor diagram showing the relationship between the phase currents and the phase voltages. Actually, do a drawing that shows all three phase voltages and all three phase currents for this load. Okay, to draw that phasor diagram, it should look like this. I will draw the three phase voltages first. Voltages will be listed V to N at 0 degrees. VB to N is the next phase voltage at 240 degrees. Phase C to N is the third voltage at 120 degrees. That's the three voltages for this phasor diagram. And if the supply is 208 volts, then we always look at supply or source or generator voltage. They just give us one voltage. It is almost always the line voltage. They're pretty clear about it being phase voltage when it's phase voltage. So the supply voltage that we have for this load is 208 volts. That means the phase voltage, the formula we use to find the phase voltage, V phase equals V line divided by root 3, 208, divided by the root of 3 is 120 volts per phase. So our voltage per phase is 120 volts. I could label that on my phasor diagram. So the three phases have the phase voltages on them. Now, to determine our phase currents, we simply take the resistance or impedance of each phase and divide it by the phase voltage divided by that resistance will give us the current. I equals E over R, or E over Z. And so the phase current for each phase, for phase A, the phase current IA, it's actually IA to N, but phase current and line current are the same thing in a Y. So if I take the phase voltage divided by the phase resistance, IA is 120 divided by 15, 120 volts divided by 15 ohms, which is 8 amps. The current in B, IB, is 120 volts divided by 20 ohms, which is 6 amps. The current in phase C is 120 volts, IC, 120 volts divided by 12 ohms, which is 10 amps. So we have the three phase or currents for this load. Now I want to put them on the phasor diagram. So to look at this phasor diagram for this load, the phase voltage for phase A to N is 120 volts. It has a pure resistor in it. And the relationship between voltage and current for a purely resistive load is in phase. So that means this 8 amps of current is right in phase with the phase voltage. IA is 8 amps, right at 100, or right at 0 degrees. For phase B to N, we have, for an inductive load, which is what this coil is, the current lags the voltage. So we need to know what angle the current is going to lag the voltage by. If I go inverse cos 0.866, your calculator will give you an angle of 30 degrees. So it means that the current in phase B to N lags the voltage by 30 degrees. The voltage is at 240 degrees. If we're lagging, we're behind. The phases always rotate counterclockwise, sorry. So if this is where the voltage is, for the current to be behind it, it has to be 30 degrees behind, which will give me an angle of IB 6 amps at an angle of 240 minus 30 degrees is 210 degrees. So the current for phase B is at 210 degrees. Phase C is a purely resistive load. So again, the current and the voltage are right in phase. So my current of 10 amps in phase C is right in phase with the voltage. C is 10 amps at 120 degrees. Okay, that's what the phasor diagram looks like for this load. Now, if we were to want to find the neutral current from this point, to find the neutral current of this system, we have to draw a horizontal vertical chart to break each of these phase currents into the horizontal and vertical values they have. And we take that horizontal and vertical chart to find our total current in the circuit. So pause the recording at this point and draw out your horizontal and vertical chart for this load to determine the neutral current. Okay, I need to make a bit of room. So I am going to make a bit of room. So I'm going to get rid of or erase my load diagram so I can show you what the horizontal and vertical chart would look like. Okay, to figure out our neutral current, this horizontal and vertical chart that we draw is fairly straightforward. Simply go all I want to do is break each of these phase currents into the horizontal and vertical values. And the way I do that is I just take the current at the angle that it's at and multiply by the cosine of that angle for the horizontal component, multiply that current by the sine of the angle for the vertical component of the current. If I start with phase current A, IA, phasor line current IA, it is 8 amps times cosine of 0 degrees will give me the horizontal part. 8 amps times sine of 0 degrees will give me the vertical part. You can just calculate that on your calculator. 8 amps times cosine 0 degrees, 8 amps times sine 0 degrees will give you those two values. If you look at the phasor diagram, you can see that the phase current A is completely horizontal. It's right on the 0 degree horizontal. So it's all going to be horizontal, 8 amps. None of it is going to be vertical. That's what your calculator should show you. or current B. 6 amps at 210 degrees. I want to go 6 amps times cos 210 degrees, 6 amps times sine 210 degrees. When you do those calculations on your calculator, you should get, for the horizontal part of this current, from cosine minus 5.2 amps, and you should get minus 3 for the vertical part. Current C is 10 amps. It's right in phase with the phase voltage, but it is at an angle of 120 degrees. So there are some vertical and some horizontal part to that current as well. So 10 amps times the angle it's at times the cosine of 120 degrees, 10 amps times the sine of 120 degrees. The values that you should get for that are, for the horizontal value, should be minus 5, and the vertical value should be 8.66. And at this point, all we do is add up our horizontal values for a total horizontal, add up our vertical values for a total vertical value. And of course, I just add up whichever the bigger number is, negative or positive. I take that bigger negative number, subtract the positive in this case, because they're going in opposite directions if it's negative or positive. So minus 5, minus 5.2, minus 10.2, minus 8 should give me minus 2.2 for a total horizontal value. 8.66 minus 3 should give me a total vertical value of 5.66. So that's how we use the horizontal and vertical chart to calculate our total horizontal and vertical values for this neutral current that we're looking for. The last step to find that neutral current now is I take my horizontal and vertical values and I just construct a triangle. So I just make a right angle triangle. The total horizontal value is minus 2.2. The total vertical value is 5.66. And I am just looking for I'm just looking for the hypotenuse of this triangle. So it's just Pythagoras theorem. It's going to be C. Of course, our hypotenuse is going to be the square root of a squared plus b squared. Do that on your calculator. What you should come up with for a neutral current is 6.07 amps. And that's how you find the neutral current for this unbalanced load. That's about as hard a problem as they can ask. The neutral, in order to balance this load out, the neutral would be carrying a current of 6.07 amps. Hopefully that helps you understand how to do these problems. You'll see another one or two of them as recordings, and hopefully this helps you understand how to do unbalanced Y loads. Thank you.
Let's end this baby.